Hello and welcome. In this video I'll be covering section 4.1, which is over polynomial functions and modeling. My goal for you by the end of the video is to be able to determine the behavior of a graph of a polynomial function using the leading term test, to be able to factor a polynomial function and find the zeros as well as their multiplicities, and to be able to use a graphing calculator to graph a polynomial function and find its real number zeros, its relative maximum and minimum values, and its domain and range. So we'll start with defining what a polynomial function is. Technically, you've had some experience with these. You just maybe have not necessarily used the word polynomial to describe them, but all of the quadratics that you had earlier this year as well as last year are considered polynomials. Even a linear function is considered a polynomial function. So as far as a definition to be able to account for all of the different types of polynomials, notice it gets a little complex here, but really the, I guess, bare bones of what's happening with this is, notice each term I have a number, this a with a subscript n, where it can potentially be a different number, hence why the subscript n minus 1, n minus 2, and so on and so forth would continue. So this ... just basically means continue or follow that pattern. That's probably a better way of doing that. But it's allowing us to have some coefficient in front, so a number multiplying an x, and then each of them have a different power. So notice the first term here being a power of n, everything beyond that has n minus 1, then n minus 2, and I would continue on, so n minus 3, n minus 4, and so on and so forth, until I get to the last two terms, which should be a power of 1, and then notice this technically I could say it has like a power of 0 on the x, but anything to a power of 0 would just equal 1, so that part I can technically drop. So it starts with the highest power, and if I write it in what's called descending order, meaning they start with the highest power and count down as I go, that then creates this idea of what's called a polynomial function. So again, you've had experience with this. Probably the most recent is dealing with a quadratic, where usually we write the higher power or the x squared on the first term, then have the middle term be our x term and our last term be the constant term. So really it would have been starting right where I have that arrow where it says follow pattern. That really would be where a quadratic is. So this definition, as you can see, is just accounting for what if the power was, say, like a power of 7. Well, technically I'd have a power of 7 on the first term, then the next one I'd have a power of 6 potentially, then a power of 5 and power of 4, and so on and so forth, until I get to the very last term, which would be a constant or a term that doesn't have an x attached to it. So all of the coefficients in this case, in order for it to truly be a polynomial, do have to be real numbers. So they can be rational or irrational. That does not matter. They just need to be in the real number system. So I should not see any i's or imaginary numbers. And then all of the exponents do need to be whole numbers. So that basically means I should not have any negatives. So no negative powers. And I also should have no rational powers, meaning I should not have any fractions up in the exponent area. All of those should just be nice positive whole numbers, with the exception of the very last one. Technically it would be x to a power of 0, but I cannot have any decimals, fractions, negatives, all of those. If you ever see any negative or fraction or any of those types of things on an x as an exponent, then at that point you would be able to make the conclusion that we're not dealing with a polynomial function. Now, some terminology to kind of get used to is the number in front of that highest power term, this a subscript n, is what's called the leading coefficient. So you can always think of the leading coefficient as the number in front of the highest powered term. Then that value of that power on that highest powered term, which notice that was the power on x, is what we actually call the degree of that specific polynomial. So for quadratics, all quadratics have a degree of 2 because that's the highest power we would see. So to try and attempt to, I guess, give you a little visual of what these polynomial functions look like, we'll go ahead and start with one that we're familiar with, called the quadratic function again. So this is just one random sample expression or example of this particular type of polynomial. notice we would be able to, just by looking at what we have here, this is a quadratic again because I notice that the power of 2 is the highest power, which again, remember we call this number right here, which again this was also written in descending order, would be our degree that we could identify as 2, and then if I needed the leading coefficient, that would be the number in front of this term, which if there isn't a number there, it's implied that there would be like a 1 right there. So the leading coefficient for this example would be a 1. Now, as far as some terminology that we've had from our past, hopefully we recognize finding the zeros, which would be, if I were to factor this and set it equal to 0, it would be the two solutions I get from setting each parenthesis or each factor equal to 0, hence the -1 and the +3. We then can interpret that as actual ordered pairs and call the x-intercepts a -1, 0, as well as a +3, 0. A y-intercept would be like plugging 0 in, so what's kind of nice with polynomial functions is if it's in the proper format, that very last number should be what we call the y-intercept, or whatever the constant is the y-intercept. So notice that's where the 0, -3 is coming from. And then other things, just looking at our graph, a minimum in this case would be our low point, so it would be the vertex of this particular one. The value happens to be a -4 at the x value of +1. It does continue to increase without bound as shown by the arrows, so there is no actual maximum. The domain happens to be all real numbers, and then the range happens to be everything. Again, range goes with y values, so it would be everything from the y value of our vertex, or the minimum, which was -4, but it's a part of the graph, so included with a bracket, as you can see here. And then it goes up forever, so -4, infinity. Again, with the bracket on -4, and infinity always has parentheses because it's technically not a number, it's more of an idea. Now, a different type of function that we probably have a lot less experience with is something called a cubic function. So it would be, if we look at our function over here, it's written in polynomial form here in this first line, and it is in descending order, where the highest power is first, and then it counts down from there. So once again, we could look at this and go, whatever the highest power is, that's the degree. So all cubic functions are functions that have a degree of 3. And again, if I wanted to identify or just practice identifying the leading coefficient, it's whatever number is in front of that specific term. If you don't see a number, just like the last example, it would have a value of 1. So as we can see with this one, we had the ability to, I guess, factor it. Not that we, at this point in time, know how to do that factoring. That's what this chapter will involve. But they provided the factored version of it for us, so that allows us to identify our zeros, again, by setting each parenthesis equal to 0, which then I can interpret as ordered pairs or as x-intercepts by putting those numbers, 0 for each one. The y-intercept, once again, matches our constant at the end, so our y-intercept for this one would be that 0, -12. And then everything from here, looking at our graph, I have a relative minimum at a low point, so that looks like the y value of -20.7 at the x value of 1.4. Then a relative maximum is a high point, so off a little bit further to the left, a value of 12.6 when the x value is -2.7. And as we can see with this one, domain is all real numbers once again, because the arrows do continue on forever to the left and right, as well as forever up and down, so our range actually happens to be all real numbers as well. So again, this is one that we have not had as much experience with, but hopefully by the end of this section, we'll kind of get used to being able to identify what the shapes of these types of functions will, I guess, look like, and try and hopefully by the end of it start connecting some of the, I guess, special names for the functions, such as quadratic, or in this case, a cubic. So to give just a couple more visuals, just to, again, try and solidify the concept, if I just went through and just said, let's identify what kind of function each of these are, as well as what the degree and leading coefficient happen to be. So for this first one here, again, I see that there's a power of 2, so that's what we call a quadratic function. And again, it's because the degree is 2. And if we want to practice again the leading coefficient idea, it's the number in front of the x squared term, or the highest power term, which in this case that would be yet another 1. Moving on to the next one, which is just a perfectly horizontal line. This function actually does have a name. It's just called the constant function. And the constant function for this actually is something that we would say has a degree of 0, because if we were to attach an x to that -3, it would be a power of 0, hence why its degree is 0. The leading coefficient in this scenario happens to actually just be the one number I see, which is the -3. Moving on to the third one, notice the highest power I see for this one is a power of 3. This was the last example. We called that a cubic function. And again, the way I know that is if the highest power is a 3, which we call the degree, and the leading coefficient for this one now is the number in front of that term, which this actually has a 2 in front of it, so my leading coefficient would be 2. The very last one is one we haven't talked about. This one has a power of 4. The special name for this one is called a quartic. And again, quartics are ones or polynomials that specifically have a degree of 4. And in this case, it's got a leading coefficient. If we were to look at the number in front of that highest power term, in this case, it looks like it would be a -1. And there we have it. So again, there are 4 kind of special names that in your assignment I'd like you guys to be able to identify are the constant, the quadratic, the cubic, and the quartic. If you just kind of think quarter has 4 quarters make $1. The quart, hopefully that kind of beginning or that root of that word will kind of connect with a power of 4 having that special name quartic. Now, as far as some examples of functions that we would not call polynomials, an absolute value function, so a few of these we should have at least a little bit of, familiarity with, but a absolute value function is technically one that is not a polynomial function. So if we ever saw an absolute value somewhere in a list of terms, then at that point we could also say this is not a polynomial. If we ever see radical signs, like this second example, radicals are also not included in this polynomial definition. If I saw powers that were fractions, such as this one, x to the power of 4/5, that turns into something that's not a polynomial. And the very last one, if I have division by x, or any x in a denominator for that matter, that cannot reduce, that then would imply that there must be a negative exponent. And at that point, I would be able to say that's not a polynomial. So each of these, if we kind of look at what are the kind of overlying things that let us know that we don't have polynomials here, well, the first and third one here, the absolute value and the one with the power of 4/5, notice those have a pretty sharp edge to them. The second one, notice it actually doesn't go forever left. And then the very last one, it actually has a complete break in the graph. So anytime if you visually see sharp edges, or it doesn't go forever left and right, or there's a break, at that point you can say, I must not be looking at a polynomial because, as we'll see in the next slide, we have to be not only continuous on its entire domain, but it also has to be nice and smooth, meaning no sharp edges. So again, to reiterate just what I finished that one with, polynomial functions do have to be continuous, meaning no breaks, no holes, nothing like that, and it does have to actually have a domain of all real numbers, meaning going forever to the left and forever to the right. So that radical example from the previous slide, since that didn't go forever to the left, was our idea, or the way that we would be able to recognize just visually that's not a polynomial. The other thing is I have to be a nice and smooth graph, so when it comes to if you plot points, know that you're always supposed to just kind of nicely curve through all of the points that you plot. We should never, ever, ever create any sort of sharp edges when it comes to, creating these graphs. So it's always a nice and smooth curve as I pass through all the points. So the next thing we'll talk about is what's called the leading term test. This actually is going to be very applicable not only in this class, but even just moving forward. So that first term, or that highest power term, notice this x to a power of n is going to essentially, again, represent, that's the highest power term, and then the an, or a subscript n, is just representing the coefficient on that. Notice we have the ability, just by looking at that one single term, to determine what my arrows should do. So anytime my degree, in other words, if the degree happens to be even, so notice these two words, even and odd, are talking about the value of n. So since that's also the same thing as what we call the degree, if my degree is even, notice with our two pictures here, my arrows will always point the same direction. Then it turns into what's true about the leading coefficient. Well, if the leading coefficient is positive, it's going to open up towards the positives. In other words, both arrows will point up. If that leading coefficient happened to be less than 0, meaning it was negative, then at that point, notice both arrows actually point down, or it opens towards the negatives, which again should hopefully not be too big of a stretch, because an x squared graph was one that opened up, whereas a negative x squared graph was one that opened down. So we've already kind of looked at this in a way. We just haven't necessarily called it a leading term test because we have kind of stopped at a power of 2. This now allows us to expand further to powers that are higher than 2 and still at least understand what the arrows at the end are supposed to do. Now, odd degrees, as we can see with the two examples here on the bottom, the odd degrees, the arrows will always point opposite directions. So even just a basic like y equals x, the power on x is an odd number, power of 1, or a degree of 1, that then would turn into something that would be arrows pointing opposite directions, which every single line that you have graphed, so long as it had a slope, did have arrows that pointed opposite directions. So again, hopefully that's not too big of a stretch. And the fact that positive slopes went up to the right and down to the left is hopefully something that we've also connected, whereas a negative slope would be one that goes up to the left and down to the right. So I personally always just like thinking in terms of what is the slope, what is the, I guess, the leading coefficient. If it comes back positive, I just think a positive slope, so I'd make it come up my page from left to right. And if it had a negative slope, I'd make it come down my page from left to right. Now notice each of these have these little squiggles here in the middle. That just means the leading term test doesn't really tell me much about what's happening in between. That's what a little bit further analysis that we'll, I guess, discover later on in the chapter will actually kind of fill in the blank for the jagged little part there. That's just representing, I don't know what happens in between. It's just more, I want the leading term to tell me what the arrows on the far left and far right should do, which really is what this, as x goes to infinity, this is talking about the right arrow, and as x goes to negative infinity, that's talking about the left arrow, if you really wanted to try and break down in the notes what those two statements mean. But again, every single polynomial, since it goes from negative infinity to positive infinity, meaning it goes as far left and as far right as possible, the end arrow really is, or the end arrows are really just what happens on the left, what happens on the right. And at that point, we could say a statement like f of x, or the y value goes to infinity or goes to negative infinity, depending on if it's going up or going down appropriately. So to show how to apply that leading term test, let's go ahead and just work through a couple of examples. Each of the graphs at the bottom do match one of the functions that's being presented here. So it's more just a matter of let's identify what we know, and based upon what we saw with the previous slide, what should be true. So for letter A, it has a degree of 4, meaning the highest power was 4. So since that has a power that's even, I know that the arrows are going to point the same direction. So they're either both going to point up or they're both going to point down. So then I focus my attention on what number is in front of it. Well, 3 is a positive number, so that means it's going to open towards positive. So if I look at all of my options down at the bottom, which one happens to have 2 arrows that both point up? Looks like option D, or letter D, happens to be what would match that. So I would be able to say that this one must be my 3x to the 4th minus 2x cubed plus 3. And the fact that our plus 3 at the end represents the y-intercept and it's going through the y-axis at positive 3 was a second thing that kind of helped us identify maybe out of those 4 options which one is potentially what we got. We move on to letter B. Notice with this one I have a degree that's 3. So that means that they're going to point opposite directions. So odd and opposite is one way you can kind of remember that. They both start with O. And then the leading coefficient in this case is negative. So I would just think in terms of what's a negative slope look like? Well, a negative slope should go up to the left, but then down to the right. So if I look at all my options, which one happens to be pointing up on the left side, but then down on the right side? It looks like option B So this one, option B, must be my negative 5x cubed minus x squared plus 4x and then plus 2. And again, that plus 2 could be a secondary thing we could use, looking for which graph goes through the y-axis at positive 2, and wouldn't you know it, that's the only graph out of the 4. Moving on to letter C. Letter C wants us to identify which one is x to the 5th. So again, that's an odd power, so they're going to point opposite directions. And then the leading coefficient, even though there isn't a number there, would be implied to be a positive one. So that's going to be pointing opposite directions and go like it's a positive slope. So that means it would have to go down to the left and up to the right. For that example, well, let's look for which one does that. Looks like letter A is the one that matches that. So this one would be my x to the 5th plus my 1/4 x, and then plus 1. So process of elimination kind of tells us that the part D of this is going to be graph C, but let's just think in terms of, let's say we hadn't answered the other ones. Look at the parts that we need to identify. Our degree, the highest power is 6, so that's an even number, so I know they're pointing this same direction. And then the leading coefficient here in front is a negative 1, so that means it's going to be like it's both pointing down. And as we can see, option C was the only one that had both arrows point down. So hopefully this leading coefficient test, you can kind of see how easy it is to apply as far as just what should I know about the arrows, because all I really have to do is just look at what is the degree and what's the leading coefficient. Even degrees, again, just to reiterate, point the same direction. Odd degrees point opposite directions. And then positive ones behave like they go towards positive values or they increase like a positive slope, whereas negative values open towards negatives or they have a negative slope. So you can kind of rely on some of your prior experience with what we have. And the next slide here just kind of confirms our answers here. Our leading term was what we really were focusing our attention on. Since the degree was even, they both pointed the same direction, and the sign of that was positive, so that was the one that pointed up for both arrows, and so on and so forth. So again, this is more just to kind of nicely organize what I had on the previous slide. Now, earlier in this video, I already kind of breached on the concept of finding zeros, and it's specifically when it's in factored forms. To find a zero, you essentially just set the function equal to 0. And then what we can then conclude, as mentioned earlier, is that that 0 would be able to be written in a ordered pair format to then represent what we would call the x-intercept of the graph. So for this example here, notice it's giving us a function that's been fully factored. It looks like I have actually the same factor repeated. This x minus 2, I have 3 different times here. So we could group that together and make it a power of 3. What's nice is even when there's a power outside the parenthesis like that, I still just set what's inside equal to 0. So I'd have x minus 2 equals 0. And then it looks like the only other factor I have is an x plus 1 that would need to be set equal to 0. And so add 2 for the first one, I would get one of my zeros is going to be positive 2. And it looks like subtract 1 on the second one, so x would equal negative 1. And so I can group it together and just say my zeros would be those two values. If I wanted them again in x-intercept format, I could then say that it would be 2, 0 as well as negative 1, 0. So again, kind of the difference between how I write these. Zeros are just single numbers, whereas intercepts are always an ordered pair. So we always want to make sure that we recognize what the question is asking us to identify and fit the formatting appropriately for what they want. Now that last example, notice we had one of the factors have a power that was outside. So what that power outside actually would be is what we call the multiplicity. So multiplicity is essentially just how many times is this factor actually a factor of the polynomial. So notice it's basically saying if k is the largest power on the parentheses, so we're getting rid of anything that's even one more than k. So if that power was, or if k equaled 4, there wouldn't be any other parentheses that happen to be either a 5 or a 6 or a 7 on that factor. So again, it's really, this is more semantics. It's just if we have it in fully factored and combined format, whatever the power is on that parenthesis is what we call the multiplicity. Now, if that multiplicity happens to be an odd number, then what's going to happen is graphically it will physically cross over the x-axis. And it's kind of peculiar with this that if the, I guess as it crosses over the x-axis, it actually behaves just like that power would be. So if it was like a power of 3, what it would do. So let's say I had a 0 right here that had a multiplicity of 1. It would just go kind of straight through like it was linear. Let's say there was another 0 over here that had a multiplicity that was maybe like a 3 or a 5 or something bigger than 1. What it does is it actually behaves like that power function. So a cubic function is one that kind of, I don't know, makes a little s in a way as it goes through that point. Would be an example of what that could potentially look like. So this would be like a multiplicity of 1, whereas this would be like a multiplicity of 3 or 5 or 7 or anything, and so on and so forth. Anything bigger than 1, essentially, as it passes through the x-axis, it will just have that little curvature to it. So the easiest way to kind of think of it is if it's higher than 1, it's just going to kind of curve or flatten instead of just go directly through. But regardless, it still does physically cross over the x-axis at that value. Now, if k is even, so notice the second situation is what if k was even, then at that point it actually just touches the x-axis. So one example would be like x squared. That actually has a 0 of 0, or x equals 0, but then it has this power of 2, which makes it an even multiplicity, or a multiplicity of 2. And if we think of what that graph actually looks like, notice it actually just bounces off the x-axis at that value of x equaling 0. So this one has a multiplicity of 2 because, again, that 0 would be a solution, technically twice if you want to think of it that way. And so at that point, since that's an even number, I know that it's just actually going to be what's called tangent to the x-axis. But basically the easier way to think of it, I think, is just it touches the x-axis and bounces right back off. So this value that we have, this value of k, again, is what's called the multiplicity. So if you ever have a question, identify what the multiplicity of one of the zeros, or all of the zeros for that matter, happen to be. We just look for any power outside of a parenthesis that factor happened to, or that 0 happened to be coming from, as far as which factor I was actually setting equal to 0. Now, as far as some statements we can say about zeros, some generalized ways that we can think of this is if I know I have a polynomial, meaning all of the powers are whole numbers and all of my coefficients happen to be real. I don't see any sharp edges graphically, I don't see any breaks graphically. If I know that I have a polynomial function and I can identify the degree, which again is the highest power, if that happens to be larger than 1, it has to, or potentially or equal to 1, then it has to have at least 1 0. Whether that happens to be a real or imaginary number does not matter. At most, it will have whatever that highest power is. So if I had a polynomial that was a degree of 5, I know I have at most 5 zeros, and it could be a combination of real numbers as well as imaginary numbers. Now, all real zeros that we identify are physically what we call an x-intercept, which means I can actually physically see where it exists on a graph. Any zeros that say when I set it equal to 0, I get an imaginary solution, meaning maybe I had to use like quadratic formula and I was taking a square root of a negative number, those ones I actually physically cannot see on a graph. So imaginary zeros at this point really are just things that, yes, we can identify algebraically speaking, we can find what their values are. It's just when it comes to making a graph, they really don't have much of an application for what we have. So let's go ahead and work through a few examples here just to kind of see how we would handle some of these types of questions that you'll see in your practice. So this one, again, it wants us to identify our zeros. So basically, I want to set this equal to 0 and try and somehow, some way, get what those values would be. Well, what's kind of tricky about this is it's not presented in the factored form. So anytime I have 4 terms like this, one option to try is to just do that whole concept of factoring by grouping. So again, with a minus in front of this second one, remember we still keep that minus with that number, but I keep a plus in between because I know it's not a product quite yet. Then I take out whatever they have in common. So with this first grouping, they have x squared in common, which then leaves me an x minus 2. in the parenthesis. The second one, for sure, I'll take out a negative because that first term was negative. And it looks like 9 would go into both 9 and 18. So if I took negative 9 out, that would leave me a positive x on this first term, and a negative 9 when I divide it out of an 18 would actually leave a negative 2 in its spot. And the way that we can now identify that this factor by grouping idea is working is, notice the parenthesis I got for both of these happen to match. So one of the factors is that x minus 2, and then the other one I have now x squared minus 9, which looks like that's a quadratic I should be able to actually solve. I guess I had my equal sign on the other side, so I'll go ahead and stay consistent. Now for this quadratic, notice the middle term is missing, so that would mean like the b value must be 0, or as we hopefully will get to a point that we're confident with, this would actually just turn into a conjugate pair when we multiply. That way the middle term does cancel, so x plus 3, x minus 3, because I want it, after all, multiplied to a negative 9, but I want it to be perfect opposite numbers such that that middle term is missing. And that turns into, again, a phrase that we have recognized, hopefully from prior classes, that's called a conjugate pair. So now if I set each of those equal to 0, my zeros for this problem would be, well, the first one, it would be add 2 over to the other side, so positive 2. The middle one, it looks like I would have to subtract 3, so that would give me a negative 3. And then the last parenthesis, it looks like I would add 3 to move it over, which would be a positive 3. So there's my 3 zeros for this problem. Now why I shouldn't be too surprised that I got 3 zeros is, again, the degree originally was 3, so that means I had at most, from the previous statement, at most 3 zeros, and it was greater than 1, so I knew there was going to be at least 1 0. Now did any of those zeros repeat? In other words, were there any multiplicities? Well, technically, yes, there are multiplicities. They just all happen to be multiplicities of 1. So if I actually had a problem that asked for what is the multiplicity of each of these, I would just maybe underneath or off to the side or right after each one just say, well, each multiplicity is 1, which then means graphically I'm expecting it at these numbers, I guess my graph to actually cross through or just kind of go straight through the x-axis at whatever these numbers are. And why I know there wouldn't be any curvature is because none of those were powers that were, or multiplicities that were greater than 1. In other words, there wouldn't be any curvature as it goes through. We'll go ahead and try another example of this concept. Now notice this one, I don't have 4 terms, so I can't do the factor by grouping, but since this middle power of 2 is exactly half of the highest power, which was 4, the first power, I know this tells me that I can have at most 4 zeros. Doesn't mean I'm guaranteed to get 4, but I have at most 4 zeros. And this actually is in what we would call quadratic form. So one way we can deal with this is we could just let y equal the x squared. So I could rewrite this now as like y squared plus 4y minus 45. So it's a little bit more familiar for us. But again, I'm trying to find zeros, so it's going to be set equal to 0. I'd then look for what pair of numbers will multiply to that constant, that negative 45. So this would be kind of it looks like most of you like doing it using the diamond factor strategy. So I want to multiply to the negative 45, but I want to add to a 4. Well, since that ends in a 5, for sure 5 goes into it, so that would be my first instinct. It looks like 9 times 5 would make that happen. If I made the 9 positive and the 5 negative, that should accomplish the adding up to a positive 4. So that would give me y plus 9 as one factor, and y take away 5 as my other factor, and again still setting equal to 0. So if I set each of those equal to 0, I get negative 9 and positive 5. However, I'm not trying to solve for y, I'm actually trying to solve for x. So I would actually want to set or replace the y with x, or just set x squared equal to each of those. So x squared equals negative 9 and x squared equals positive 5. The step for each of these that I would have to do is taking a square root, and since I'm the one that's introducing the square root, I need to remember a plus or minus symbol right off the bat. This first one, though, it's a square root of a negative, so I know that's going to create an imaginary number. The square root of 9, though, actually is a nice perfect square, so I could say that that would just become a plus or minus 3i. So even though those came back as imaginary numbers, that just means graphically I wouldn't really be able to do anything with that value, but still technically that's 2 zeros that I've identified. So I've got 2 so far, and it looks like with the second one I'm taking a square root again, so I need to remember a plus or minus symbol. So there's 2 more answers from this one. And then the square root of 5 doesn't actually simplify very nice, but it is at least a positive number, so these are imaginary for the plus or minus 3i, whereas I have 2 real ones over here with the plus or minus the square root of 5. So 2 imaginary, 2 real for a total of 4, which that's good. That's the most I could have gotten anyway. So when it comes to identifying my zeros, there's my 4 that I got. Only 2 of them, the plus or minus rad 5, are ones that physically I could see graphically. If I were to either graph this using maybe Desmos or a graphing calculator, or physically actually plot things out. Another type of problem that you'll have in your practice or your homework is going to be to just utilize substitution to determine if a list of numbers, so in this case it's given us 3 different numbers to test, to see if it actually is a 0 for the function. So these, as far as just what do I need to do, it's really as simple as just take the number and plug it in. If it's truly a 0 of the function, then the result I get should be 0. So this first one's going to be 2 times 2 cubed minus 3 times 2 squared plus 2 plus 6. So if I were to simplify each of these values, 2 cubed is 8, doubled would be 16, then minus 2 squared is 4, 4 times 3, that would be 12, so minus 12, then plus 2 plus 6. So if I were to start just from the left and move my way to the right, 16 take away 12 would be 4, plus 2 would be 6, plus 6 would be 12. That didn't equal 0, so this one would be a no for 2. As far as is that truly a 0, yes or no, I would go with no since I didn't get 0. Let's go ahead and try the next number, 3. So that's going to be 2 times 3 cubed minus 3 times 3 squared plus 3 plus 6. So simplifying this, 3 cubed is 27, 27 doubled would be 54, minus 3 squared is 9, 9 times 3 would be 27, then plus 3 and plus 6, so again working from left to right I'd have 54, take away 27, which is 27, plus 3 is 30, plus 6 is 36. Once again I did not get 0, so no for 2 and 3. So we only got one more to try, f of negative 1 it looks like, so this would be 2 times a negative 1 cubed minus 3 times a negative 1 squared plus a negative 1, so I'm going to go ahead and actually write that as minus 1, and then plus 6, so simplifying each of these, negative 1 cubed is negative 1, times 2 is negative 2, negative 1 squared is positive 1 times a negative 3 would be a negative 3, then minus 1, and then plus 6. So let's go ahead and try this out. Negative 2 minus 3 would be negative 5. Take away one more is negative 6. Negative 6 plus 6 is in fact 0. So this one would be a yes for negative 1. So thus far, again, just as far as any time a question just says, are these zeros of this function, ultimately the easiest way to test is just plug the number in and see if you get 0 in the end. If it truly equals 0, then you can say yes. If it doesn't equal 0, you can then just say no, but technically it would be a point that we could plot. So technically this has 3 points that we just identified, 2, 12, we just identified 3, 36, and then the last one was a negative 1, 0. Notice only one of those technically came back as an x-intercept, or on the x-axis, which is why that was the only one that we actually called a quote-unquote 0. And one of the last types of problems is something that just kind of brings all of this stuff together. It says to actually find the zeros, but then also explicitly state what their multiplicity is. So I need to identify zeros, their individual multiplicity, and then it also wants me to do a secondary part for this, which is identify the leading term as well as the degree of this particular polynomial. So let's go ahead and find the zeros first. This is kind of nice that it's already in factored form. So if I set this first one equal to 0, or just x squared equal to 0, I would technically take a square root of both sides, and that would give me x equals a plus or minus 0, which really is just 0. But because of the power of 2 right on this, I could go ahead and say that the x equaling 0 has a multiplicity of 2. So what would that mean? Well, that means it would actually just touch the x-axis when it comes to graphing it. So just to kind of think ahead, we're going to get to a point where we're graphing. If we can kind of connect while we're learning this, what that graphically means is just going to touch the x-axis at that value. The next one, if I set x plus 3 equal to 0, I would subtract 3 and just get x equals negative 3. But again, that one had a power on the outside of that parenthesis as well. In this case, that power was a 2. So I could say that the x equals negative 3 is a 0. Its multiplicity happens to be 2. And again, since that's an even number, I could go ahead and think ahead to what would that mean graphically. It would just touch the x-axis. Moving on to the next one, I've got x minus 4 equaling 0 that I would need to solve. So it looks like I would just add 4 to both sides and get a solution of x equals positive 4. And in this case, my multiplicity is whatever power is outside. Well, notice I don't see a power right here, which then implies that it must be just a power of 1. So it's a multiplicity of 1, which means it would actually physically cross the x-axis at that value. And again, the value in this case is the x-intercept of 4, 0. So it's going to cross at that one again because that's an odd multiplicity. And then the very last one, x plus 1. Set that equal to 0. I would subtract 1 to get my 0 of negative 1. It has a multiplicity in this case that is equal to the power outside, which was 4, which because that's even, I know it would physically just touch the x-axis or bounce off of it if you prefer that description, but it would not actually physically cross over what's going on. So again, notice we have the ability to kind of think ahead into what would I physically expect to see on my graph when it comes to what I would, I guess, have as an end result if the question asked me to physically graph whatever this function is. Now, as far as the second half of this problem, which says what is the leading term, the way that I do a leading term is I basically just take whatever the first thing is, or whatever the highest power is from each of those. First, I would apply the power to that, and then I just multiply those things together. So in this case, it looks like I'd have 4 things. So I'd have x squared that would multiply with another x squared from the second parenthesis, again taking the power outside and just applying it to that, because that would be the highest possible power that could come out of that. Next one would be times an x, and then the last one would be times an x to the 4th. Hopefully we remember exponent rules would just be, since the bases are all the same, it would just be add our exponent. So it would be 2 plus 2, which is 4, plus 1, which is 5, plus 4, which is 9. So our leading term for this one, since all of the coefficients also were 1, would actually just be this x to the 9th, which then means the degree of this is 9. Which, if we think back to the beginning, that means my arrows, if I wanted to actually think about what the shape of the graph would be, it would point down to the left and up to the right because it's an odd power, and then all of this extra info that I identified with the zeros kind of would let me know what happens in this middle area right here. But as far as the end behavior, or the what the arrows should do, that's a degree of 9 with a leading coefficient that's positive. So again, point opposite directions and go up the page from left to right. And so we have the ability to kind of analyze these a little bit more intensely just by thinking of what would that highest power be. Hopefully that made sense how I came up with that. Now, had there been a number inside, I would have to apply the power on the parenthesis to that number as well and multiply it with any other numbers that were in front. What was nice with this one, though, is all the coefficients were 1, which then meant the leading coefficient, when it was all said and done, would also just be a 1. But anyway, hopefully this video has been helpful in just introducing the concept of what a polynomial is. If you do have questions, though, please don't be shy to ask, either myself or Miss Bass. As always, I appreciate you taking the time watching the video, and we'll catch you next time.